When you've taken a satellite image and run it through a classification algorithm, you've created a map that has labels on it. This could be typically labels that indicate the land cover or the land use of each pixel. So we imagine that we've created something like this here. And we have a bunch of labels. I'm going to label this forest, forest, forest. Maybe there's a lake up here, and we have classified that as water pixels. We have more forest over here. Maybe we have some agriculture that abuts both of those. And we have, let's say we have an urban area down here. If you want to show this map to someone and you want them to have an appropriate amount of trust in that map, you need to let them know how accurate it is. And this is not obvious just from the classification result itself. So to assess the accuracy of a map, we need to actually test it. We do this by checking the classification of a set of pixels against independent validation data. These independent validation data, they are ideally created by someone going to the location that your map is for with a GPS, locating maybe this pixel exactly here, going there and noting down what is the actual land cover of this pixel. So we might go and we check this pixel, check this pixel, this pixel, this pixel, this pixel, and here. We should aim to check pixels that are distributed across all of the classes in your classification. Otherwise, we may get a good idea of how accurately the water was classified, but have no idea how accurately the urban areas were classified. So once we've done this checking, we can establish a very simple list of these points. So we can have the classification here, and then we could call it reality here. And so if we go with our example above, we have 2 water pixels that we went to and looked what was there in reality. And let's imagine that we were pretty good at classifying those, so those are actually water. We had 2 urban pixels that we classified, and let's say one of them was actually agriculture. Maybe it was a suburban area and it was right on the edge, and we got that one wrong. We have 3 agriculture pixels. Let's say they were all correctly classified. And we have 2 forest pixels. And maybe one of those was actually also incorrectly classified because it was actually agriculture. Maybe it was a very dense crop that had some characteristics that made it look more like forest. This is the basis for the calculation of accuracy metrics. So to calculate accuracy metrics, we typically take all this data and we put them in a slightly different format called the confusion matrix. I'm going to try to make it not so confusing. Let's imagine that we have all of our classifications out here and I'm going to call them validation data. That's a more commonly used term for it. And we have our classes, so we have water, agriculture, forests, and urban here. And we have the same classes and in the same order here. The order doesn't matter as long as it's the same along both axes here. So now we have this matrix set up, and we can take the data that we have over here and we can fill it in. So we look at, of the pixels that were classified as water, we have 2 of them. How many of those were actually water? 2 of them. That's good. How many of them were actually agriculture? None of them. How many were actually forest? None of them. And actually urban areas? None of them. And we add a total column at the end here. So we get a total value of 2. This is good. This is the kind of thing that we like to see. Of the pixels that we classified as agriculture, 3 of them were actually agriculture. None of them were water. None of them were forest. None of them were urban. So this is also exactly what we want to see. Of the 2 pixels that we classified as forest, only 1 was forest and 1 was agriculture. None were water. None were urban. So we get a total of 2 here. And of the urban pixels, one was urban, one was agriculture, none of the others here. And now we can sum up the rows, the columns here too. We get 2, 5, 1, and 1. And the sum total of all of these is 9. So this is just a different way of looking at the same data. But what we can do now is we can calculate 3 different accuracy metrics quite easily. The first one that I want to mention is the user accuracy. I always think of this as sort of the picnic accuracy. If I want to go to a forested area for a picnic, and I use my map to try to find a forested area, the user accuracy answers the question, how likely am I to actually end up in a forest if I let myself be guided by the map? User accuracies are calculated along the rows of this table here. So the way we calculate it for a given class, we take the number of correctly classified pixels. Let's use the picnic as an example. So we want to look at the 1 correctly classified pixel for forest compared to the 2 pixels that we know what the actual class is and that were classified as forest. So that's 1 out of 2. So the user accuracy for forest is 50%. That's not very impressive. I'm 50%. I have a 50% probability of ending up in a forest if I take my map and go to a pixel classified as forest. I'm just as likely to end up in an agricultural field. We can do the same, obviously, for agriculture. We get 100%, so that's great. Water, 100%. And urban areas also only 50. So those are the user accuracies. We can also calculate what's called the producer accuracy. This looks at if a pixel is actually water, how likely was it to come out as water in the map? How likely was it to be classified as water? So that we calculate using the columns. For water, we have 2 correctly classified water pixels out of 2 total. So we get for our producer accuracies here, we get 100% for water. We get for agriculture, we get 3 out of 5 total, which is 60%. For forest, we get 1 out of 1, so that's 100%. And for urban, we get 1 out of 1 as well, so that's 100%. So if we compare the user and producer accuracies, we get an interesting pattern. We see that the producer accuracies are generally higher, but that they're very variable. The urban area had 50% user accuracy and 100% producer accuracy. If you see a big gap between the user and producer accuracies for a given class, you should be slightly worried. That tells you that there's a bias in your map. So for example, the bias in this map, which happens to be the same for the forest and the urban classes, is that we are likely to have more pixels classified as forest or urban than exist in reality. Right? We have twice the number of pixels classified as forest than what exists in reality. So that's the kind of bias that we probably want to avoid. The last thing we want to look at in terms of accuracy, and the term that's most typically reported, is what's called the overall accuracy. This provides the answer to the map, to the question, just how accurate is my map? In general, not considering any specific class, just broadly speaking. To figure that out, you take all the values along the diagonal here, and you divide them by the sum total. So in this case, we got 2 plus 3 plus 1 plus 1, that's 7, divided by 9. So we have an overall accuracy of, I don't know what that is, but 7 out of 9. We typically express it in percentages. So this tells you essentially if you go to any pixel on the map, you have a 7 out of 9 chance that it's actually correctly classified. Ideally, you should report all of these measures because they combine to tell you how accurate the map is, and more importantly, they combine to tell other people how accurate your map is. If you do see very low accuracies, you should probably consider going in and updating your map to make it better before you finalize your accuracy assessment and you report on it. The last thing I want to mention is I kept the numbers small here so that the calculations were right, or were easy. They're also right. Ideally, rule of thumb says you should have at least 50 data points for each class. So if you do go out with a car and a GPS and you go out and check a bunch of pixels in your classified map, that's a good general rule to follow. This isn't always possible. If you have made maps that are for areas that are really inaccessible, in Canada this is typically for the north, but it could also just be really far away from a road. It could be in the ocean. All kinds of inaccessible. It could be on Mars. It could be, very, very inaccessible places. You don't have the luxury of going there with a GPS and a notebook to note down what is where in reality. What you can do in that case is that you can use other imagery that you are confident that you can look at and visually interpret what the reality is. Because as good as classification algorithms are, they're still typically not as good as the human eye. So if you run a classification on an image and then you zoom into a set of pixels that you have selected, ideally at random, you can probably see what the true class for a given pixel is, at least if the imagery that you're looking at is of sufficiently high resolution. So those are your two options. You can use field data, where you go out and look at what is actually there, or you can use high resolution imagery. Ideally get 50 points for each class, run through this process, report on the user accuracies for each class, producer accuracies for each class, overall accuracy for the image as a whole. There are other accuracy metrics that are used for unique situations, and you can learn about those as you need to.